Welcome to Tumul online classes. In this session, we'll see the new concept. Concept is self-inductance. This concept can be explained on the basis of Faraday laws of electromagnetic induction. What we know, just I can remind what is meant by Faraday laws. Wherever magnetic flux linked with the coil changes and EMF induced in the coil, induced EMF continue as long as magnetic flux changes. Right? And what about second law, Faraday's second law? The magnitude of induced EMF directly proportional to magnetic flux linked with the coil. I mean, wherever magnetic flux linked with the coil changes, an EMF induced in the coil. Today's concept, self-inductance. This concept can be explained on the basis of electromagnetic induction. I mean, on the basis of Faraday's laws. Yeah. To understand the concept of self-inductance, I can take this is nothing but coil. The coil contains many number of turns. Simply I can take this is nothing but self-inductance coil. Simply I can call it solenoid. Now to understand concept of self-inductance, let us take now current can flow in this coil. This much current can flow and this current is constant. What I am taking? Wherever current can flow in this coil and this current is constant. Wherever this current is constant, no such extra phenomena is observed. But wherever in this coil or in this conductor, wherever current can increase, what I will do just I want to increase the current. Wherever current can increase, around it variable magnetic field is produced. Due to variable magnetic field, magnetic flux is produced. I mean changing magnetic flux produced. Wherever magnetic flux changes, an EMF induced in the coil. What I am saying directly, wherever changing current is produced in the coil, in this coil due to that changing current, magnetic field also changes. Wherever magnetic flux changes, EMF induced. This much EMF induced in the coil due to increase in current. How this EMF induced? EMF induced in the coil due to changing in current. This induced EMF again opposes the growth of this current. I mean this current comes from battery. Shall I take? I can take this is nothing but battery. This is nothing but battery. From this battery variable current can flow. Due to variable current, magnetic flux changes. Due to changing in magnetic flux, and EMF induced in this coil. Right. This induced EMF again opposes the growth of the current. Now second situation I will take. Again I will take same coil. Simply I can take same coil I can take. This is the same coil I will take. In this coil, now this time I want to decrease the current, not increase. Just I want to decrease the current. Due to decrease in current, variable magnetic flux also produce. Because what? Due to decrease in current, magnetic field decrease. Due to decrease in magnetic field, magnetic flux also decrease. Due to decrease in magnetic field, also EMF induced in this coil. But this induced EMF again opposes the growth, again opposes the decay of this battery current. Because this current again comes from battery. Shall I take? I mean, wherever current increase, EMF induced, the induced EMF opposes the growth of the current. Wherever current decrease in the coil, there also EMF produced, but this EMF helps the decay of the current. I mean, wherever current can decay, due to decay of current, it acts along the direction of applied current. Then, what phenomena you observe? Wherever current can changes in the coil and opposing EMF produce. Wherever current can changes and opposing EMF produce. This phenomena I can call self-inductance. Okay, how to define self-inductance? The phenomenon of opposing EMF. The phenomenon of opposing EMF induced in coil. Opposing EMF induced in coil. Opposing EMF induced in coil due to changing current in same coil. Due to changing current in same coil. due to changing current in same coil. Due to changing in current in same coil. Then little bit we will see how current can changes, how EMF can induce. See here. We know that wherever current can flow in this coil, in this direction current can flow. So in this coil there is magnetic field. What is magnetic field value? B is equal to mu naught I divided by 2R, where R represents radius of the coil, right? Wherever current can increase, magnetic flux also increase, magnetic field also increase. Wherever magnetic field is increased, what is flux? Flux is equal to B dot A, right or wrong? What we know? Wherever current can increases in the coil, magnetic field also increase. Due to increase in magnetic field, magnetic flux also increase. Wherever magnetic flux is increased, in this coil EMF induce. EMF can induce. The induced EMF now opposes the growth of this current according to Lenz's law. You know the concept of Lenz's law. The polarity or the direction of induced EMF opposes the changes produces it. This induced EMF opposes the growth of this current. It is one case. In second case, what we will do? Now wherever current can decreases in this coil current can decrease. Wherever current can decrease, magnetic field decrease. Wherever magnetic field decrease, what is magnetic flux? Magnetic flux also decrease. Now due to decrease in magnetic flux, in this case EMF induced, the induced EMF opposes the decrease in current or opposes the decay of the current. I mean, wherever current changes in this coil, magnetic flux linked over the coil changes. Due to that coil, EMF induced, the induced EMF either oppose the growth of the current and opposes the decay of the current. Then, how current can increase, in what way magnetic flux can changes? That phenomena we observe. So here, from this what you can take? Wherever current increase, current can increase, I can increase. Wherever current increase, what will change? Magnetic field will change. Magnetic field increase. Due to increase in magnetic field, what is magnetic flux? Magnetic flux also increase. Then what relation we observed? Magnetic flux linked with the coil directly proportional to current. What we observed? Wherever current increase, magnetic field increase. Due to increase in magnetic field, magnetic flux also increase. Right? What you observed from this? Magnetic flux linked with the coil directly proportional to current, or magnetic flux linked with the coil equal to constant into current, where constant L is called self-inductance of the coil. What is L here? Self-inductance of the coil. Wherever magnetic flux linked with the coil changes and EMF induced in the coil. According to Faraday, what you can take? The magnitude of induced EMF is directly proportional to rate of change of magnetic flux along with negative sign. Here what is negative sign? Whatever induced EMF, that induced EMF opposes the change in magnetic flux. Right? Induced EMF opposes the growth of the current, or induced EMF opposes the decay of the current. Right? Now again, but we know that is phi is equal to L into I. Then what is induced EMF? Induced EMF is equal to what value? Minus of d by dt of what value? L into I. So this is very important relation when current can changes in the coil. Wherever current can changes in the coil and magnetic field can produce. Or you can modify this equation. Here L is constant. Wherever L is constant, what you observe? Minus L into how much? Di divided by dt. This is important relation. Wherever current can changes in coil and EMF can produce. Then I said that this constant L we are calling coefficient of self-inductance. Coefficient of self-inductance. Coefficient of self-inductance, or simply I can call self-inductance. Right? Question is, how this self-inductance will depend? How self-inductance will depend, that we will explain in detail later. Initially, we will see what is the definition of coefficient of self-inductance. See here, wherever current in the coil either increase or by decrease. By increase in current and by decrease in current, this EMF can induce. Right? Consider in this coil current changes by the rate 1 ampere per second. Current changes by 1 ampere per second. Current changes by 1 ampere per second. Wherever current changes by 1 ampere per second, what you observe is equal to what value? L. Just again take magnitude of L. See here, what is negative sign indicates? Negative sign indicates direction of induced EMF opposes the change in current, either increase or decrease. Look at here. Then we got E is equal to L. From the second call, what is mean by self-inductance of the coil? Self-inductance of the coil is nearly equal to EMF induced in the coil if a current changes by the rate of 1 ampere per second. I mean, if the current changes by 1 ampere per second, self-inductance or coefficient of self-inductance equal to EMF induced in the coil. This we are calling coefficient of self-inductance. But the coefficient of self-inductance, let us see what about SI unit. Again, what is alternating definition of coefficient of self-inductance? That we'll see. Look at here. We know that this self-inductance has SI unit. How to write from this L? L is equal to what value? E into dt. E into dt divided by what value? Di. Right? So L is equal to E. E nothing but volt. E nothing but volt. T is nothing but time. That is second. Volt divided by current. Current is nothing but ampere. What is SI unit? Volt second per ampere. Volt per ampere second. This we are calling SI unit of the self-inductance. But instead of this unit, self-inductance or coefficient of self-inductance can be measured in terms of Henry. In terms of Henry. Then, how to define Henry or how to define coefficient of self-inductance? See here. Again from this equation, what I can take? If the case current changes in the coil by 1 ampere per second. Current changes in the coil by 1 ampere per second. Then, what you can taking? E is equal to L. I mean, if di by dt is equal to 1 and E is equal to what value? E is equal to 1 volt. E is equal to 1 volt. E is equal to 1 volt. Di by dt. Di by dt is equal to what value? 1 volt. Then what you observe? L is equal to 1 Henry. Look at this relation. If di by dt is equal to 1, E is equal to 1 volt, then L is equal to 1 Henry. Again from this I can define what is meaning of coefficient of self-inductance. How to define? Coefficient of self-inductance is said to be 1 Henry if current changes by the rate 1 ampere per second such that it induced an EMF of 1 volt in the coil. How to define? Coefficient of self-inductance is said to be 1 Henry if current changes by the rate 1 ampere per second, it induced an EMF of 1 volt in the coil. This is alternating definition of coefficient of self-inductance. Then we will see on what factor coefficient of self-inductance depends. Directly we will go self-inductance of a solenoid. That concept we will see. Very simple. Shall I remove it? Our next concept is coefficient of self-inductance of solenoid. We will take a solenoid. From the solenoid we will see in detail how self-inductance of the coil will depends. On what factor it depends. In detail we will see here. Our next concept is coefficient of self-inductance. Self-inductance of a solenoid. Self-inductance of solenoid. Right? Now we will take a solenoid, the coil with many number of turns. Coil with many number of turns. This I can call solenoid. Right or wrong? This solenoid has length. How much length of the solenoid? Consider L is nothing but length of the solenoid. It contains total number of turns. How it contain? Consider it contain total number of turns, N value. It contain area A. Look at me, it contain area A. Right or wrong? Now in this coil consider current can increase. Current can increase. Wherever current can increase, around it variable magnetic field can produce. Due to variable magnetic field, magnetic flux also produce. The produced magnetic field, it induces an EMF. This EMF always opposes the growth of this current. Right thing? What you observed? What you observe here? Magnetic flux linked with the coil. Magnetic flux linked with the coil directly proportional to current. See here, what you observe? Magnetic flux linked with the coil. Magnetic flux linked with the coil directly proportional to current. But if this coil contains so many number of turns, for one turn only this value, it contains so many turns. For number of turns, just I want to multiply by n value. Then the product of number of turns and changing flux, this we are calling flux linkage. Right? The linkage in flux directly proportional to current, or else I can write change in magnetic flux equal to constant into current. Right around this. Then again from this what you observed? What is changing in magnetic flux, or what is self-inductance L? L is equal to how much? N into phi divided by what value? That is I. So I call it is equation number 1. Right around. But we know flux formula. What is change in flux? Change in flux is equal to what value? Magnetic field into area. Due to this current, magnetic field can produce. Due to changing in magnetic field, magnetic flux also changes. But wherever current can flow in this coil, around it magnetic field is there. What is magnetic field of the solenoid? Magnetic field of the solenoid can be written in this way. B is equal to what value? N mu naught I. This is magnetic field in the core of the solenoid. This concept you all learnt in moving charges and magnetism. Now shall I call? This is nothing but equation number 2. But what is small n? Here small n represent number of turns per unit length. How it is then? See here. B is equal to what value? Number of turns per unit length. Mu naught I whole divided by what value? This is the L. Number of turns per unit length. Total number of turns per unit length, this we are calling small n. Then what about this equation 2? Flux is equal to what value? Flux B. B this value. N mu naught I into A whole divided by L value. Equation number 3. Right? Now, from equation 3, put equation 3 in equation 2. What will get? What will get directly? Put equation 3 in equation 1. What will get? See here. L is equal to, N keep it up same. What is phi? This value? Phi mean N into mu naught I into A whole divided by I into how much? That is L. This I get cancelled. What is remaining? Self-inductance. N into N, that becomes N square. Mu naught area divided by what value? Length value. What it is? Self-inductance of the solenoid. From this what you conclude? Self-inductance of the solenoid, it is not depends on current, not depends on change in magnetic flux. Self-inductance of the coil, it depends on its geometry. Geometry mean it depends on square of number of turns, depends on area of the each coil, and depends on length of the coil. How much length decrease, how much number of turns increase, how much area increase, that much self-inductance will increase. I mean, if the current changes by 1 ampere per second, 2 ampere per second, 3 ampere per second, EMF will induce, right? But the self-inductance of the coil, it not depends on current, not depends on changing current. It depends only on the geometry of the coil, depends on nature of the coil. So that self-inductance of the coil depends on geometry, of the coil, geometry, and depends on nature of the coil. Depends on nature of the coil. This is what? Self-inductance of the solenoid. But we know that wherever current can increase in the coil, around it changing magnetic field produces. Due to changing magnetic flux also produce. Due to changing in magnetic flux, some energy can stored in an inductor. Our next concept is energy stored in an inductor. What are calling this? Self-inductance of solenoid. Due to this self-inductance, how much energy can store in an inductor? That concept we will see. Our concept is directly energy stored in an inductor. See here. Concept is energy stored in an inductor. This concept we will see in detail. What is energy stored in an inductor? Right. Again, shall I take a coil? The coil with many number of turns. This I can call solenoid. Right. In the solenoid, consider this much amount of current can increase. Direction of current must be like this. This much current can increase. Right. Wherever current can increase in the coil, due to increase in coil, variable magnetic flux can produce. The variable magnetic flux, it induces an EMF E. Again and again I am saying, this induced EMF opposes the growth of the current. If the current decrease, this EMF acts along the direction of applied current. Now this EMF acting opposite to direction of current, but wherever current can decrease, the induced EMF acts along the direction of current. I mean, the produced EMF opposes the cause produces it according to Lenz law. Right. Question is, whenever current can changes in the coil, variable magnetic field produced. That variable magnetic field can stored in the inductor in the form of magnetic field. That we are calling energy stored in an inductor. See here. We know that wherever current can increase in the coil, magnetic flux changes. What do you observe? Change in magnetic flux directly proportional to current. Right? Or change in magnetic flux equal to constant into current. This constant we are calling self-inductance. According to Faraday's second law, magnitude of induced EMF directly proportional to rate of change of magnetic flux along with negative sign. See here, what is negative sign indicates? Direction of induced EMF opposes the cause produces it. Then simply I can take magnitude. In magnitude, how to take? In magnitude I can take E is equal to d phi divided by dt. Simply I can call this the equation number 1. What about this? Equation number 2. Right or wrong? Now, I can take again from equation 1 d by dt of phi. Phi is equal to L into I. In magnitude I am taking. Here L is constant. Then what EMF is observed in the coil? Due to changing in current. Due to changing in current, E is equal to L into what value? di by dt. Let us call it the equation number 3. Equation number 3 I can call. Right. Now, question is, how much energy can store in an inductor due to changing in current? We know the definition of EMF. What is the definition of EMF? E is equal to what value? Work done per unit positive charge. Right. Then what about this equation? E is equal to dw by dq. Look at me. dw divided by what value? dq. Right. Is equal to how much? L into di divided by dt. Right or wrong? We know current. Definition of the current. Current is the rate of flow of charge. I is equal to how much? I is equal to dq divided by dt. What is dq again? This dq is equal to how much? dq is equal to I into dt. Then what about this equation? Shall I call? I can call this the equation number 4 now. Look at me. dq is equal to I into dt. Keep this here. dw is equal to dq. dq is equal to how much? It is I into dt equal to L into di divided by dt. Right. This dt dt get cancelled. Then what is remaining? This I bring this side. What will get? dw is equal to Li into di. I into di. But the current can changes from 0 to some ampere. Let us take current can changes from 0 to 2 ampere, 0 to 4 ampere, 0 to 5 ampere. See here how the current can changes now. The current can changes from 0 to I naught ampere. Remember, 0 to 2 ampere, 0 to 3 ampere, 0 to 4 ampere, like this current can changes. Wherever current changes in this ratio, what about this value? Integration will take. How it is? Look at me, how will take integration directly? Integration of what value? Integration of dw, right? L is constant. L is constant here. L constant means integration from where to where? 0 to I naught. I into how much? di. I into di. Then how will take? Integration of dw, that is nothing but w. L kept up same. Integration, this value is 1. Then what about integration of this value? I square by 2 from where to where? From 0 to I naught. From 0 to I naught mean directly how to take? Work done is equal to L kept up same. How much? I naught square by 2 minus 0 square by 2. 0 square by 2 is equal to 0. Then this work is equal to L I naught square by 2. Directly this work is stored as energy. What energy? E is equal to what value? L I naught square divided by 2. This we are taking. I mean, this much energy can stored in an inductor. Wherever current can changes in the coil. Current can changes in the coil. Electric energy changes. Due to changing in electric energy, magnetic energy changes. Due to changing in magnetic energy, the energy can stored in the inductor in the form of magnetic field. So that in an inductor, how much energy can stored? E is equal to half L I naught square. I mean directly, how much current will increase in this coil? How much current will increase? That much magnetic field increase. Wherever magnetic field increase, more energy can store. Directly, if the coil having high inductance, more current can flow in the coil, then more amount of energy can store in an inductor. Simply, this inductance will increase. When inductor is said to be pure inductor? Inductor said to be pure if the coil having high inductance and low resistance. High inductance means the coil must be contain large number of turns, it contain less amount of length, I mean smaller the length, more the area, more the number of turns, inductance can increase. How the inductance can increase? By increasing number of turns, by increasing short length, right? By increasing bigger area of the coil, then inductance can increase, right? And wherever more current can flow in this coil, energy can store. So this is what energy stored in an inductor. The remaining concept we will see in the next session. Thank you, students.